So we are going to be talking mostly about velocity today, which brings us to probably the most, in my opinion, one of the most tested things on, for whatever reason, on the exam, like guaranteed FRQ in some way, shape, or form, and that is particle motion. Probably multiple choice questions about it regarding acceleration, velocity, and position. All right, let's start first. Obviously, rates of change, we're talking about what? Slope. And if I'm talking about instantaneous rates of change, which I am, then I'm talking about, okay, which is the derivative, right? The first derivative here. So this is going to be lots of derivatives. So before we actually start, a lot of times we have to rewrite equations in terms of other variables. So I just want to take a minute, talk about how we do that, and then how that impacts us taking the derivative, rewriting in terms of. This is number 4, by the way, in your homework. A square of side length s, so a square whose side length is s, is inscribed in a circle with radius r. How could I write the area of the circle as a how could I write the area of the square, the area of the square in terms of the radius of the circle? So I want the area of the square, but I want it using, the only variable that I want to use is the radius of the circle. Any ideas how I'm going to do that? Do y'all remember what inscribed means? Did y'all learn that in geometry? So inscribed means it's completely enclosed inside this circle. All the vertices sit. Terrible. All the vertices sit on the circle itself, and it forms a square. So we know the radius, which goes from the center to any point on the circle, right? So essentially the length from the center of the circle to one of the vertices of the square is length r. But how do you find the actual area of a square? Length times width. But since it's a square, those are both the same. And since the side of this one is s, what would the area of that square be? S squared, right? Are we all okay there? I can't write it that way, though, because they asked me to write it in terms of the radius, which means only using the radius to write the area of the square. Is that possible? It probably is. Can you think of anything I might be able to do? Anybody? Come on, y'all can do this. My picture is not great. Would that help me any? Maybe. How might that help me? It's half of the side, okay. So you're saying this is 1/2 s. Is that what you mean? Or this is, okay. So I've got this, both of them are, okay, so I've got this triangle like this. This is R, right? What would this angle be? Any guesses? 45. It's bisecting that because it's inscribed in this circle. That's 45, it only leaves 45 for the other. I'm in a special right triangle situation, right? Now could you write this side length using only the variable r? How? So if these are the same, this is the square root of 2. This is r times square root of 2. So what would that side length be? You need to go backwards on it. What would you have to do? Okay, if you've got, if this is 1, this is the square root of 2, right? How do you go backwards to get here? Divide by the square root of 2. If to go forward you multiply, then to go backwards you divide, right? So this is actually going to be r divided by the square root of 2, which is r times the square root of 2 over 2. Why isn't what now? So this is not the radius. Look, it doesn't come all the way over. And this is the same length as that because it's a 45, 45, 90. So the hypotenuse is the radius of the circle, but not the legs. No, I was just saying that this is a leg times the square root of 2 is how you get the hypotenuse. Don't. Anytime you have a 45, 45, 90 triangle, like if this was x, then this would be x times the square root of 2, whatever the leg is. And then, of course, if you go backwards on it, so if this was x, then this would be x times the square root of 2 over 2, because you'd have to divide by the square root of 2. Does that make sense? Okay. So here I've got this side length, and you told me that this is a half of s, right? So would you agree that 2 of these make up this? So s is the same thing as 2 of these. Agree or disagree? So what's the side length? Whatever the radius is times the square root of 2. Well, remember what our whole goal was in the beginning. Our goal was to find the area of the square using only the radius variable. So writing the area in terms of the radius of the circle. Can you do it now? Certainly hope so, because the area of a square is, we said it's side squared. Can't use the s, but I can replace the s with this because they're the same thing, right? So the area of the square is really does that make sense? This was, I picked the hardest one for us to do together that had so much geometry embedded in it. Y'all look lost. So if you take r times the square root of 2 and you square it, because you're multiplying in here, you can distribute to both. R squared, and then the square root of 2 squared is just 2. Bless you. All right, so there it is, written in terms of the radius. Now tell me, what is the instantaneous rate of change of the area with respect to the radius? What in the world does that mean? The instantaneous rate of change of the area in terms of the radius. This is a whole lot of words for things you already know how to do. What'd you say? 4R. That's it. So we're going to say that the derivative of A with respect to R, does that make sense why I wrote dA dr? R is my independent variable. Okay, so dA dr is 4R. That is the derivative here. Let me see if you really understand. If my radius, let's say that my radius is in inches. I think that's what they say. They don't say, but let's say my radius is in inches. What would my instantaneous rate of change units be? Inches what? Inches squared per inch. How are you getting that, Khalil? What units are is A in? Inches squared. Area is always square inches, right? Or square whatever unit. Radius is in inches, so it's inches squared per inch. Does that make sense? A good, easy way for you to always figure out what the units are. Remember, a lot of times if you don't have this in your question, they're not going to give you your answer point, and that stinks. Evaluate the rate of change when R is 1 and then when R is 8. So the rate of change when R is 1 and then do the rate of change when R is 8. Not even a whole lot of work to do here, right? Where are you plugging 1 in? Are you plugging 1 into dAdr or into A? dAdr. So this is what? Oh, I feel like y'all are half dead. At inches squared per inch. How about when R is 8? 32 square inches per inch. What in the world does that mean? You understand that clearly we don't. For every 4 inches of area, that's right, keep going. Right. Does that make sense to y'all? That's the rate that the area is increasing. For every inch that the radius increases, it gives it 4 square inches more area, essentially. Y'all okay there? So the area is increasing 4 square inches for every inch the radius is increasing. Remember when we're talking about IROC, we're always talking about a rate every time. Shall we do another one of these for y'all? Yeah. Let's do number 3 then. We haven't even got to the particle motion yet. This one was hard because of the inscribed and everything else. But let's see. You try this one. Write the area of an equilateral triangle. Equilateral triangle as a function of its side S. Find the area of a triangle. How do we find the area of a triangle? Any triangle. 1/2 base times height, right? Everybody knows that. We remember that. What does it mean to be an equilateral triangle? All sides are the same. So let's call the side length S because that's what they tell us to call it, right? Essentially, I would say the S and the base are the same. Would you agree? Because all the sides. So B and S, same thing. I'm going to drop down a perpendicular bisector here, right? Because this is how I find my H. But the question is, how in the world am I going to find this value in terms of S? So I'm going to pull this triangle out on its own for just a minute. All of the, and this is not S anymore, this is going to be half of S, do you agree? Because it bisects that whenever I drop the height down. What else do I know? What other value do I know? Say again? The hypotenuse, how do you know? That's exactly right. It's an equilateral triangle, it's one of the sides, so it's S. Oh, that's right, I'm thinking 36.9. Okay, what else do you know? If this is S, and this is S, what else do you know? It's a 30-60-90 triangle. I just said that. I didn't mean to give it away. How do you know it's a 30-60-90 triangle? It's equilateral. How many degrees are in a triangle? 180. Divide that by 3. That means this one's got to be 60, which means that only leaves 30 for this one. So now I have to go back and think, what in the world the long side, short side, this is 60, this is 30. Generally, we go from the short side, right? From the short side to the hypotenuse is twice the length, and that makes sense because it is here. But how do I get to the long leg? It's the short leg times what? That's right. Good job, Khalil. Square root of 3. Okay, that's always the pattern with 30-60-90 triangles. So now, if this is a half S and this is S, right? I need to go and always work from your short leg. It'll just make life easier. How do I go from here to here? Multiply by square root of 3. That's it. So this side is square root of 3 over 2 S. Agree or disagree? Can you now write the area of the equilateral triangle in terms of S? Well, this is the square root of 3 over 2 S. So 1/2 the base S, the height square root of 3 over 2 S. Now just clean it up a bit. This is going to be square root of 3 over 4 S squared. You okay? Y'all need a break before we do the particle mesh? Or you want to move forward? Khalil says yes. I call these my little bug problems because for some reason I always envision a little bug crawling across a number line whenever I try to envision position and where they are. So what I have is I have this equation. We always use S. I'm not real sure why we always use S, but we do as a function of time. This is my what I call my position function. It tells me over a certain amount of time where my little bug is on my number line. So if I start at 4, if I plug in 70 seconds, the little bug goes or whatever, my position function will tell me where he ends up, at what point he ends up. Maybe he ends up at 7, maybe he ends up at 0 or wherever. But it tells me where he ends up over a certain course of time as he's moving, whichever direction, however he is moving. So my starting point is going to be my S of 0 because that's when my time is 0. That's where he starts, is when he begins. For right now, we'll start at 0 to make things easier, but it does not have to be 0. Now, we have something, and this is not written on your blue sheet, and I'm not sure why. I mean, it is, but it's not written this way, so you'll need to write it. We'll reference this blue sheet a lot, especially at first. Does anybody know what displacement means? Say it again. Right. So it's your distance traveled, essentially, right? It takes into account, because even if you're moving backwards and that's a negative, it's still distance traveled. So it takes all that into account. So it tells you essentially how much you've traveled. This is written on yours as, we'll get to that in a minute. All right, so displacement is essentially it's my final position minus my initial position. I shouldn't say the total amount traveled. It's the total amount, it's the span of the difference in where I started. So it's how far, not the total distance covered, but maybe I went forwards, backwards, and I ended up an inch from where I started, then the displacement would be an inch, because that's the total difference. Does that make sense? Okay, so to find displacement, this is kind of a confusing way of looking at it, but again, I think you found, or probably have noticed, that a lot of the way we write things is really a bit confusing. I don't really want to use S. I do the function of t plus the change in t, okay, as a position. So what this really is just my final position. And from that, I subtract my initial position. This will give me displacement. This is also called average velocity. So on your blue sheet, there's two different average velocities. This is the very first one. If under that you will just write displacement, that will help you. So let me show you what I'm talking about here. Not average velocity value, but the average velocity, the change in position. What did I get this? Say again. S of t. The first average velocity. X of t, yeah, I'm sorry. We're going to work through parts of number 19 at a time. But number 19 says, a particle moves along a line so that its position at any time when t is greater than or equal to 0, which makes sense because you're not going to look at t as negative 2 seconds, is given by S of t equals t squared minus 3t plus 2. The very first question asked me to find the displacement during the first 5 seconds. Well, if I start at 0 seconds, so displacement, which is just my change in position, right? Delta means change. So my change in position is going to be my final position. So if I said over the first 5 seconds, then I'm really just doing S of 5 minus, what am I subtracting? S of what? 0. And understand what this means. If I plug 0 into that equation, that's telling me where I started. So if I'm on a ruler And then in inches, where did my bug start at time t equals 0? At 2, right? So I'm starting, my bug starts right here. Do you see why? S of 5 will tell me where he ended up, but it won't tell me how far off he is from his starting place, so how much overall distance he covered, what the change in that distance was. All right, so S of 5, which would just be 5 squared minus 3 times 5 plus 2. 25 minus 15 plus 2.
Good morning, Captain Constable. This is Mabel Wallace. Please give me your undivided attention as we reflect on the
S of 0, we've already said, is 2. So I end up at 10. 10 what? I don't know what meters. It said meters. 10 meters. So regardless of what else my little bug did, he's 10 meters off from where he started. Does that make sense to you on what? We don't use displacement a whole lot past introducing it, but I think that's why I'm struggling with it a little bit. We'll get some good stuff in this point. Yes, no, maybe so. Displacement. Do you understand what displacement is? Just, okay. How far you end up from where you started. All right, let's talk about average velocity for a minute. Average velocity. Average velocity is just change in position over change in time. If you think about this in terms of your position equation, remember I have an S of t, and we're still going to keep referencing that number 19 problem because it's easier to do this with a problem than anything else. Tell me what you're really finding. Look at your variables. Change in S divided by change in t. You're finding the slope. You're exactly right. Rise over run. This is nothing more than slope of position. That's it. That's all average velocity is. So the average velocity over the first 5 seconds. We'll say average velocity from (0 to 5). Well, what's my displacement in the first 5 seconds? We just found that. 2. And what's my change in time? How many seconds did I span from 0 to 5? So, what was it? Oh, gosh, dog it. Hey! Where did I get delta t? Delta t is just change in time, which we said it was over the course of the first 5 seconds, right? So 5 minus 0 is 5. So this would be 2. Now, any ideas on what my units would be? Oh, what? What? Wait, what? Oh, yes, I'm sorry. I couldn't hear you. I'm sorry. You're talking so quiet. Meters per second, yes. Well, this thing in my mind, I couldn't remember the 10. I remembered the 12 and the 2, and then I couldn't. Anyway, now let's pull this all together. This was average velocity, right, over the course of 5 seconds. So average velocity sounds a lot like an A rock kind of situation because I'm talking about slope. Would you agree with that? What is the velocity at 5 seconds? That was exactly what I was about to say. How'd you know? What is the instantaneous velocity at 5 seconds? Any ideas on what I could do? (32x). I don't. Oh, no, I don't even have to do all that, no, but I do know what you're talking about now. Instantaneous velocity. Okay, now to find average velocity, I took the position equation and found the slope. How do you think I could find instantaneous velocity? IROC of the position function. You're exactly right. IROC of the position function, which is nothing more than the derivative of s. So in fact, here's your very first huge position particle motion big, I can't even think of what I'm trying to say. You need to know it. The derivative of position is always equal to velocity at a point. So if I asked you for the instantaneous velocity at 5 seconds, well, that would be the velocity at 5 would be the derivative of position at 5. And my position, remember, was, this is still coming from number 19, t squared minus 3t plus 2. So the derivative, which is also the velocity, of t would just be the derivative of this. That is 2t minus 3, right? So what is the velocity at 5? 7 what? Meters per second. So you just remember this was my rate of change, so meters per second. A little bit different than my average, right? Let's take it up another notch. I just keep showing you that it's the same thing. So if you start with position, which is s, if you take the derivative of s, you get velocity. Velocity is very closely related to speed. In fact, the absolute value of velocity is the speed. Have y'all learned that before? No, you've never had that in your little math, like science classes or whatever? Maybe physics. Did y'all take physics? Okay, well, anyway. That is, I think that is on your sheet, yeah. Speed, just so you know, speed is the absolute value of velocity. It'll help you keep straight what it is you're finding. And if you think about how speed is measured when you're driving down the road, 50 miles per hour, that'll help you understand what you're finding. All right, so I go position, take the derivative, I end up at velocity. And then if I take the derivative again, yep, I'll wait on you and then tell me when you're done. Good. Are you okay? You look sad. Yeah. No, you don't. Okay. I'm resting sad face. Okay, so position. I'll write this a gajillion times to try to ingrain it in your brain. Velocity, which is the first derivative of position, so that's velocity. Then if I take that derivative one more time, so it's the second derivative of position, which is the first derivative of velocity, it will give me acceleration. And let's use our same meters per second. If position was in meters for our example, and velocity was in meters per second, what do you think the units for acceleration are? That's exactly right. Meters per second, which is meters per second squared. Yeah, okay there. Well, then what do you think the acceleration is of our same problem? I'm spelling that right. Never write out acceleration. That's an E. Y'all are no help this morning. What's the acceleration at t equals 5? How you know? And in fact, we had, what was our position was t squared minus 3t. Our velocity was 2t minus 3. Acceleration is 2. What does that tell you? The acceleration is always 2. It's got a constant acceleration. It's constantly accelerating, right? If you're in your car and you're constantly accelerating, constant pace, then what's happening? Yeah, right. Okay, what does this mean? I almost feel like we should stop there. The derivative of velocity. So the derivative of velocity would just be 2. So at any point in time over that interval, it won't be a lot. I guess I need to say this one. Remember when we talked about that little bug? He doesn't always just run forward on the ruler. Sometimes he skirts backwards too. So how do I know when he changes his direction and starts going another way? You're exactly right. Sign changes of what? Good, Zach. Sign changes of the derivative. So which is, in our case, the velocity, okay? When I'm talking about position, so direction changes when position functions, when does that change? When does the sign of the derivative change if you're looking at an original function? In other words, if I have a parabola, when does my derivative, which is my slope, where does the slope change? We've talked about this. At 0, when the slope is 0, but not necessarily 0 here, but what is it on the quadratic? The max or min, right? The vertex of the parabola. This is where it changes. So essentially, the position function changes when we have a max or a min, okay? So here my derivative is negative, here's my derivative positive. If I talk about in terms of velocity, that's where the sign changes. So really, if I want to know, well, when did he stop going this way and start going this way? What I need to do is I need to find out when he stopped. Well, he's going to stop when velocity equals 0, because that's where he's changing, right? He's either going to stop and rest, or he's going to just stop and go the other direction. Does that make sense to you? Okay, so to find out the points where he changes direction, I need to find every place that this happens, and then I need to determine the sign of the velocity there. These are what we call sign charts, and they're very, very, very helpful in determining what's going on with my function. So let's look at the same example we've been looking at. Our little bug, his position is t squared minus 3t plus 2. Okay, and we're gonna sit here on this section for a while because it's very, very important. So if you don't get everything today, do not be upset. And so my next question I found, at what values does the particle change direction? When does the particle change direction? I'm going to give you some little things to do here. The first thing you want to do is find when velocity, which velocity is the same thing as the derivative of position, find when it equals 0. Well, the derivative here.
Tom, we need juniors for the last names D through H. That's juniors, D through H. Please report to the auditorium for your pictures. Thank you.
When is velocity 0? Are we all in agreement? Do you understand that what I really found is the vertex of my parabola, right? Because that's where my derivative is 0. When the derivative is 0, the slope of the tan line is 0. So I've found a horizontal tangent. That only happens at maxes or mins. Are y'all all still with me? If not, can you at least follow that in order to find where it changes directions, I need to set the velocity to 0. Okay. All right, so here's what I'm going to do. I'm going to make a sign chart. What is a sign chart? A sign chart helps me keep straight what my function is doing as compared to its derivative. Okay, so what I'm going to do is I'm going to make this little line here. I'm going to say that this line represents my t-values. My position is going to be up top. My velocity is going to be in the bottom. And I want to label every place where my velocity is 0, because what's going to happen is when the velocity is 0, these are the potential places where my slope may be going from negative to positive or positive to negative. It may be changing. And that's what they ask me is, where is it changing direction? Now, if I come in here and I find out actually that my slope is positive everywhere, well, he never changed directions. He just stopped to take a rest at 3/2 seconds. But if it changes, then he did. He stopped it at 1.5 seconds, and then he went the other direction. So let's see what happened. So what I want to do is I want to find the signs here. In other words, is it positive or is it negative? So on this side, if you think about this like a number line, right? Here, 0's over here somewhere, and it keeps going. If you take the velocity equation and you plug in some value less than 3/2, and essentially, since this is the only place that equals 0, everything on this side is going to have the same sign. So what's something easy I could use to plug in? What's less than 3/2? 1 or 0, okay? Take the velocity equation. Where's my velocity equation? If I put 1 or 0 in there, do I get a positive or a negative number? A negative, every single time. Every single time I'm going to get a negative number. 2 times 1 minus 3 is negative. 2 times 0 minus 3 is negative. 2 times negative 5 minus 3. All of these are negative, no matter where I am. This is the point that it changes. Well, if my derivative is negative, what does that tell me about my function? What does the graph of my function look like? If you have a negative slope on the tan line, what's the function doing? Increasing or decreasing? Decreasing. It's going down. You're exactly right, because it's decreasing. How about bigger than 3/2? Positive or negative? In fact, no matter what I pick, it's always positive, which means what about my function? Does that make sense? So where do I change? The question was, at what values of t does the particle change direction? That means my little bug started walking backwards, right? Then he stopped, and then he started moving forward. Does that make sense? Sure. What if I had done this and I got positive, positive? And they asked me, when did he change direction? He never changed direction. He always moved the same way. Now, he stopped for a minute, because if I'm 0, that means he stopped. He just got tired. He started walking, got tired, stopped a second, but then he kept going. But he never backtracked. Does that make sense to you, what's going on? When is the particle So I'm talking about the position. When is the position of the particle at a minimum? When does position have its smallest value? At 3/2, right? Because it's decreasing and then increasing. Does that make sense to y'all? These are crucial, and we'll work a lot with sign charts, because that's your first introduction of a sign chart. I hope I did okay. And when position is at a minimum, where is the bug? When position is at a minimum, in fact, where is the particle, or where is our bug, when S of t is at a minimum? But where is S of t at a minimum? We just talked about that. It stopped at 3/2. So where was he at 3/2 seconds? How do I find that? Which equation? I got 3 of them. I'm so confused. To the original position. If it asks you where, it's position. Where, that's position. Every time, which is S of t. But remember, that's telling you where on that ruler that bug is. So where is the bug when S of t is at a minimum? Well, I know the minimum is 3/2, so all I'm going to do is find S of 3/2, and I'm going to plug that in. So 3/2 squared minus 3 times 3/2 plus 2. Go back to the original equation, which should tell you negative 1/4. What is my unit here? Meters. You think you can do it? You can do a little bit. We'll start Monday really writing some good. In fact, if you answer, we're going to do page 142 to 143, I think it is. We've already done 3 and 4, so do 1, 2, and then 19 through 24. For these, if you answer them,